This episode of Nova Science Now. What if somebody called you a bird brain? Wouldn't you be insulted?
Oh, great compliment.
I know.
The bird brain is a very good brain.
So good, a bird brain came up with this.
So that's Beethoven's Fifth, out of the mouth of a wood wren.
Now, these clever creatures are helping us solve the mystery of how humans learn to talk.
For an organism that is so distant from us, that's quite remarkable. Nature is playing a very slick trick right there.
And the Northern Lights, one of nature's most impressive light shows. But behind this dazzling display is a dangerous surge of energy that could kill astronauts and turn the lights off here on Earth.
I guess this is mission control.
Solar terrestrial indices.
Now a new space mission is underway to find out what triggers the spectacle and how we can avoid disaster.
3, 2, 1.
Whoa. Also, in our profile, she wanted to be a tennis star until injuries
I broke my ankle 3 times. I snapped my Achilles tendon.
forced her to change her game. Now, she's on the cutting edge of bionics.
One day, people are going to be walking around with a prosthetic hand, which nobody can tell it's prosthetic. It moves like it looks like it's controlled naturally from the brain. That's how it's going to be.
All that and more on this episode of Nova Science Now. Hello, I'm Neil deGrasse Tyson, your host of Nova Science Now. You know, the ability to speak is one of those things that makes us humans think we're special.
What?
But researchers have
Special?
struggled to figure out exactly how we got this talent.
What?
Because
Talent?
learning to use language takes a lot more than just mindlessly parroting what someone else says.
Mindless.
Now, as correspondent Chad Cohen reports, we're finding new clues in the brains of some animals who have the language ability to even rival our own.
Split infinitive.
Bonjour le chien.
It's a skill that comes naturally to even the tiniest among us. We take in sounds,
Les clés. Qui veut les clés?
repeat them,
Je fais au revoir.
and learn to talk. We're so good at it, we can even do it in more than one language.
Au revoir.
Like these little New Yorkers who are learning French even before they've mastered English.
S'il te plaît.
And yet, we still don't understand how. It's a mystery scientists are starting to unravel by studying a brain about 1,000 times smaller than our own. A brain that's gotten a really bad rap.
If someone called you a bird brain, how would you?
Oh, great compliment. The bird brain is a very good brain.
Ofer Chernikowski, one of the world's leading experts in birdsong, thinks the term bird brain is a real misnomer. In fact, he believes the key to solving the mystery of speech lies in the notes of a bird's song.
By looking at the song and see how the song develops, you can understand sometimes very basic principles of how our brain works and how our mind works.
In his lab, Ofer studies an Australian songbird called a zebrafinch.
Now you can actually see them side by side.
It turns out this tiny bird learns to sing, much like we learn to speak.
In the beginning, the bird will start singing a very faint, unstructured song, similar to babbling in human infants.
It then starts to mimic the sounds it hears from the adults around it, a lot like we do.
Can you say ham? See the ham?
So birds are vocal learners, and vocal learning is very rare in nature.
While zebrafinches learn only one song, other songbirds like canaries can learn new songs seasonally. Some hummingbirds learn songs more bug-like than bird-like. And parrots, like this one named Einstein, can even mimic other species.
Can you do a pig?
Adding new words to their repertoire all the time.
What does everybody say in Tennessee?
Einstein seems content to receive a treat for displaying his vocal talents. In the wild, though, male songbirds use their song to defend territory or to woo a mate. The guy with the best song gets the girl. But to get her, he's got to be creative.
Every individual bird has his own song, his own performance. So they imitate, but they also diverge and vary.
And in the process, create rather sophisticated melodies.
So here's a song of a veery, and let's listen to it a little. Does it sound musical to you?
Sounds like a bird.
Okay, I'll slow it down for you.
That's incredible. That's incredible. That's the same bird.
Birdsong is so elegant, it's inspired the great masters. Mozart borrowed these notes from his beloved starling. When his muse died, the distraught maestro even gave it a formal funeral and wrote a poem in its honor.
Let me play to you something and see if it reminds you of a piece of music, okay? So here is a wood wren song.
Da, 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 da. So that's Beethoven's Fifth out of the mouth of a wood wren. That's just crazy. That's just crazy.
Beethoven was really a fraud, huh?
Yeah. So which came first, though? Can you teach?
No, he came first, I can tell you that. At least a few thousand years earlier.
Duke University neurologist Eric Jarvis thinks we have a lot more in common with songbirds than first meets the ear. He's been studying bird brains and comparing them with ours.
The basic similarity between songbirds and humans is that we both have cerebral brain areas that control learned vocal behavior.
So if you look at the cerebral areas of my brain, for example, this area back here helps me understand the words I hear, whereas a little bit further up, this area helps me produce the actual words. It's taking no less than 100 muscles, by the way, just for me to be telling you this. And before I can utter a single word, that word understanding area and that word producing area need to talk to each other through some sophisticated circuitry. A songbird's brain also has areas that process and produce sound, and these areas are also connected through sophisticated circuitry.
For an organism that is so distant from us, that's quite remarkable. Nature is playing a very slick trick right there.
A trick that Dr. Santosh Helikar is using to help unravel the mystery of speech. He's exploring a troubling speech disorder.
I love
Stuttering, a condition that causes patients like Dennis to get stuck on syllables.
Initiative.
Believe it or not, Santosh thinks that some of his zebra finches have a similar problem. Yep, it appears songbirds stutter too.
A normal bird song of a zebra finch consists of a sequence of syllables that are repeated over and over again.
This is the sonogram of a normal zebra finch song. A simple melody consisting of several syllables repeated over and over again. But Santosh's stuttering birds sing like this. They get stuck on one syllable and keep repeating it over and over again. Not unlike what's happening to Dennis.
Hi Santosh, how are you? Hi Henning, how are you? Good. Yeah, I brought some birds. Oh yeah, good.
To find out why, Santosh, along with colleague Henning Voss of the Weill Medical College of Cornell, decide to scan the brains of these pint-sized stutterers. To do it, they have to adapt an fMRI machine designed for a human brain to scan one a lot smaller. Henning creates this coil to do the job. Once the tiny patient is mildly sedated, it's put inside the coil and into a soundproof box equipped with headphones. Then bird box and all are placed into the fMRI and the scanning begins.
We will see the brain from the side.
They soon pick up a signal.
This is the forebrain, the cerebellum. Here one can see midbrain and spinal cord coming out.
Right.
And the beak.
Now it's time for the entertainment portion of our program. The tiny patient is played a familiar melody, the song of its father, who first taught him how to sing. As it listens, the scanner picks up increased blood flow in the part of the brain used to process sound.
Okay, we have very nice activations, right?
Smack in the middle of the hearing center within the brain.
The scans show nice activation, but when they compare the results of these stuttering birds with scans of normal birds, they find a difference.
The stuttering bird's brain doesn't have the same pronounced activation as a normal bird has.
If I tease the initiative...
And here's where it gets really interesting. It turns out similar activation patterns are found in human stutterers. Stutterers have less activity in an area of the brain used to process sound than normal speakers do. This connection between human brains and bird brains poses yet another question for researchers. How did two distinctly different species end up with not only intriguingly similar vocal learning systems, but similar speech disorders? The answer may lie in our genes.
What?
Back in the 1990s, researchers found a genetic link to language when they discovered an English family suffering from a rare speech disorder.
Where do you live, Laura?
This family had extreme difficulty with vocalization, with moving their mouths around in the right way, with putting the sounds in the right order.
Genetic studies revealed a single gene mutation was the cause. The faulty gene, called FOXP2, was christened the language gene.
That discovery prompted myself and Constance Scharf, a longtime collaborator of mine, to examine whether or not something was similar in songbirds.
Do birds have a FOXP2 gene? Because that wasn't clear at the time.
Well, they not only found the FOXP2 gene in birds, they discovered how it influences the way a bird learns to sing.
When the young birds are learning how to imitate songs, the FOXP2 gene was going up.
This enabled cells to produce more protein.
And after learning was complete, it went down. Not only that, we found that in canaries, who can continue to learn song throughout life, at the time of the year they're learning how to imitate new songs, the FOXP2 gene goes up again.
An amazing discovery that brings with it a whole other set of questions. FOXP2 is found in just about everything from fish to yeast.
Even in flies and bees. So it's not the gene that makes us speak. It's a gene that is being used in many neighborhoods.
Eric Jarvis, for one, is committed to figuring this out. He set his sights on identifying other genes that may hold the key to why we can speak. Birds can sing, and others, even our closest relatives, cannot. It's not for lack of communication skills. Since the 1970s, researchers have demonstrated that chimps understand our words and can even answer back.
You feed me. You feed me fruit.
Chimps have this ability of sign language. They already have language with the hands. They just can't do it with the voice.
Jarvis theorizes that a few unknown genes give us something the chimps don't have. That neural circuitry connecting the word understanding area of our brain to the word producing area. Without this circuitry, he surmises, chimps can't speak.
It's not such a crazy idea to think that a few genes have to be mutated to get such a system in the brain.
A system that gives us the gift of gab, and our feathered friends inspiring melodies.
I love these little guys, but now doubly so because they are a model organism. We can seriously study them.
Whether it's through words or song, one thing's for certain. We aren't the only ones with something to say.
How about a chimpanzee?
Welcome back. A breaking story tonight. Big storm brewing. We've got a meteorologist in the field. Can you hear me?
Yes. As you can see, I'm in the thick of it out here.
Excuse me, but where are you?
I'm out in space, orbiting Earth. And believe it or not, there's some serious storms up here. And they can cause all kinds of problems down there, especially with communication systems.
Seem to be having some technical difficulties. And in the meantime, check this out. Anyone who has seen the Aurora Borealis, or Northern Lights, will tell you they're one of nature's most spectacular performances. A celestial ballet of light dancing across the night sky. But it turns out there's much more to this dazzling display than meets the eye. Because the same thing that powers the dance of the Northern Lights can also wreak havoc, exposing astronauts to deadly amounts of radiation, frying electrical systems and satellites, and overwhelming power grids, causing widespread blackouts. Problem is, no one has ever been able to agree on the exact choreography of events that gives rise to both this beauty and danger.
This has been one of the persistent and difficult questions to solve in space physics.
But now, an unusual space mission is aiming to solve this mystery once and for all, because figuring out what makes the Northern Lights dance may also hold the key to predicting these kinds of events and avoiding disaster. The Northern Lights take place more than 60 miles above Earth's surface. But they're not caused by weather on Earth. They're caused by something much less familiar, called space weather. Now, some of you may be thinking, space weather? Can't possibly rain or snow in space. I mean, you don't see astronauts shoveling out the space station, do you? Well, turns out space has its own special kind of weather, thanks to that big ball of glowing gas we call the sun. Every day, the sun spews out 1 million tons of electrically charged particles, which race away at up to 300 miles per second, forming what's known as the solar wind. Most of these particles are deflected by Earth's magnetic field, the protective shield that envelops our planet. But some sneak through and eventually collide with air molecules. When they hit oxygen, you get a red or a green glow. Nitrogen, a blue glow, creating a steady ring of lights around the north and south magnetic poles. But sometimes, the whole process goes berserk. Huge amounts of energy from the solar wind build up in Earth's magnetic field and then are released in a sudden explosion called a substorm. And you can tell when that happens because the Northern Lights start to dance.
So the eruption of the aurora really corresponds to an eruption of a substorm, an energy release out in space.
But where do these violent storms begin? To find out, a team has launched a mission called Themis, consisting of 5 identical satellites. Wait a minute, 5 satellites? Isn't that overkill? Well, to see why they needed that many, think of a tsunami. A single buoy in the ocean can tell you if a tsunami has taken place. But if you want to figure out which way the wave is moving and how fast, you need multiple buoys. And it's the same with substorms, except instead of buoys in the ocean, the Themis mission is using satellites. The goal of the mission is to figure out exactly where substorms start. And once every 4 days, the satellites enter the region of space where substorms occur to detect if they erupt near Earth or farther out in the magnetic field. The Themis mission is operated at the University of California at Berkeley. What am I looking at?
Now you can see...
I see the Earth in the middle.
That's right, and the 5 satellite orbits off to the right. This covers 4 days worth of orbit tracks.
And it's very clear when they all line up.
Exactly.
Themis is named for the Greek goddess of justice, that blindfolded lady that holds the scales on courthouses. And just as the goddess weighed competing explanations to determine the truth, the Themis mission will try to discover the truth about substorms. The evidence will be gathered by huge antennas on each satellite. And to see how they packed 5 of these into just one rocket, I paid a visit to one of the guys who designed them. So where have you brought me? What is this place?
Well, so this is the mechanical engineering lab.
One antenna was designed like a kind of high-tech jack-in-the-box. It was nicknamed the Death Spike, for reasons that would soon become obvious.
And when I pull this string, it's going to release...
Can I give you a countdown?
Yes, go ahead.
Okay, ready? 5, 4, 3, 2, 1. Whoa.
So as you can see, about 10 foot up.
And with these antennas deployed, the team hopes the satellites will be in the right place at the right time to catch a substorm in action.
It's like we've laid this trap. We've gone to the jungle and we're waiting for the tiger.
And missions like Themis come not a moment too soon. The sun works on an 11-year cycle, its activity level rising and falling with the number of magnetic disturbances called sunspots visible on the surface. Over the years, people have tried to link the sunspot cycle to everything from skirt lengths to stock prices. But one thing we know it does relate to is space weather. And right now we're entering a new solar cycle, which will peak between 2011 and 2012. When that happens, the first to know about it will be the nation's Space Weather Prediction Center in Boulder, Colorado. Here, a special breed of weathermen keep their eyes on the sun 24/7.
Solar terrestrial indices for 29...
Drawing on observations, data from satellites, experience, and a strong dose of intuition, they issue alerts and warnings, as well as a daily space weather forecast.
No space weather storms are expected for the next 24 hours.
So who needs a space weather forecast? Well, NASA for one. And everyone from utility companies to satellite operators would like even longer range forecasts, like we have for weather on Earth. But that's a tall order.
Space weather is much more difficult to predict than terrestrial weather. First of all, the volume of space between us and the sun is 93 million miles cubed in size. It's huge.
To get a handle on such an enormous volume, space physicists just up the road from the Prediction Center are trying to build computer models to forecast space weather. The results look like this. A simulation predicting how hard the solar wind's blowing, the direction of the magnetic field, and the appearance of the northern lights. But today, these models can only make forecasts about an hour in advance.
We are, in essence, back at where weather forecasting was in the 1950s. We're just kind of getting started into this system and making progress. But it's a kind of exciting time to be in this because you're at the beginning of a new capability and providing these tools.
Meanwhile, to gather information to improve these tools, the Themis satellites continue lining up every 4 days in Earth's magnetic field, lying in wait for substorms. It'd be fun to be on one of these satellites as you sort of come into alignment.
And watch one of these auroras break up at the same time.
No, I don't want to be there for that. It takes 2 days for all the data from the outermost satellite to download to Earth. And it will take months or even years to analyze. But in previous alignments, the team's already been lucky, snaring several substorms.
This is when the 3 substorms took place. One took place here, the next one about an hour later, and the next one about yet another hour later.
That's these peaks.
These peaks.
That's the bleeding edge of the frontier of science.
That is exactly right.
And if their luck holds, they'll catch enough substorms in this 2-year mission to figure out the physics needed to improve space weather prediction and to solve the mystery of what makes the aurora dance.
Uva ugo ni pat kiyoyat. Ila ni atururut. Ila ni tusang naktok ni pat. Ilangit inyupet okaperurot animelanun iligoranun inyusakanip lugich. Nagaka ingilran pirsot. Sivulengisa pitkutinip lugich. Uva ugo ni pat kiyoyat. Ila ni atururut. Ila ni tusang naktok ni pat inyuk aput mi isukatak-totun. Toduk-dok-tutin Nova Science Mik Akupak.
Here at Nova Science Now, we've always considered the epitome of cool to be smart and into science. But sometimes kids think they have to choose between being smart and being popular. Well, in this episode's profile, you'll meet a popular kid who finally decided to embrace her inner geek. And now, she's reaping the rewards. At age 37, Yoki Matsuoka is finally not afraid to stand out. At the University of Washington, Yoki is a pioneer in neurobotics, an emerging field that combines neuroscience with building robots. Yoki won the MacArthur Genius Award for her visionary work.
It's easy to describe Star Wars and say, remember that scene where where Luke goes and then moves the hand around and it looks like a real hand, but there's a little door that opens on the arm and then they're all mechanical pieces moving around, and that's what I make.
Thanks to her, people who need them will someday have prosthetic hands that will look and move like real human hands. And what makes Yoki's hands so remarkable is that it will be controlled directly by the human brain.
I don't think Yoki's ever just one of the crowd. She's doing stuff that's very different from what other people are doing, and I think she enjoys being out there on the edge.
Growing up in Tokyo, Japan, Yoki always knew somewhere deep down she was not like other kids.
I knew that I wasn't the same as everybody else. Somehow, something was different.
Then she found the most unlikely of soulmates.
When I first saw John McEnroe, I bet I was about 5 or 8. He had a personality that was different from other people. He really stood out. I think that's why he was called the bad boy of tennis.
At age 11, Yoki started playing tennis too. But as a girl in Japan, she knew she could never be like John McEnroe.
Oh yeah, it's not acceptable to be bold. It's not acceptable to really express your opinions, especially as a girl. I think I was afraid to show that I was different, and I admired people who could show that they are different and not be afraid of it.
Tennis became Yoki's obsession and her identity, and she was good. When Yoki was 16, her parents, both former athletes, sent Yoki to the United States with hope of her becoming a professional tennis player.
I was really pushing and then playing a lot of tennis, maybe 3.5 hours of tennis and 1 hour conditioning every day.
And at her new high school in Palm Bay, Florida, she tried hard to fit in. She studied the show Friends for hours on end to learn English and how to act like the perfect American girl. She even changed the spelling of her name.
My real name is Yoko, and I often got, expressions saying, "Oh, you're Yoko, just like Yoko Ono." And I changed my last letter from O to Y to Yoki.
Yoki was fitting in. But when she began to do well in math and science, she started to stand out in a way she didn't like.
Whenever I received an award, whether it's a science award or math award, my friends would come over and say, you got an award, so you are smart? And then I would say, no, that's just a mistake. I don't know anything about it. I don't know what they're thinking, but since they're going to give me an award, I'll just take it. It sounded like a geek or a nerd, and I just didn't want to be that. As girls, we all wanted to be accepted as pretty girls or athletic girls, not the science girls or math girls. If people perceive me as an airhead, then that gained my popularity. I get to have cool friends.
Yoki was so afraid of looking like a nerd that she wouldn't be seen carrying a book.
I even got to the point where I pretended that I was never studying and then just, hid in a library for 2 days before the test, and then I studied. I had to live a double life. I never tried to just stop learning math and science. I just secretly did it.
On the tennis court, Yoki was on the fast track to becoming a pro. She even reached the qualifying rounds for Wimbledon. But Yoki's body could not withstand the stress.
The first tennis injury, I sprained my ankle so bad that basically the bone came off with it. Since then, almost every year, I had a pretty severe injury. I broke my ankle 3 times. I snapped my Achilles tendon. I snapped my patella tendon. I hurt my back. I had split quad muscles.
She secretly dreamt of creating a robotic tennis partner to help her strengthen her body and keep training through her injuries.
And I thought, well, I know some science and then I know some robotics. Wouldn't that be great if I can build a robot that I have, have multiple knobs and said, well, today this person should have this kind of spin on the serve, or somebody else who just would not miss any balls, but would not hit really hard. Push me just the right amount every day. So that's really the first time I started thinking that robotic tennis partner would be great.
Due to injuries, Yoki never played professional tennis. But she did get to build robots. At MIT, she studied under the world-famous roboticist Rodney Brooks.
So in principle, I see no reason that we can't build a robot eventually that is as capable as a human being.
Like John McEnroe, Rodney was known as the bad boy in his world.
Rod is called Bad Boy Robotics because he also has an attitude. He thinks wild ideas that other people won't think of and won't accept.
I went around reveling in being different and reveling in telling everyone else they were wrong.
Rodney was working on COG, a cutting-edge humanoid robot.
Different body parts were up for grab. Which body part would you like to work on? And I said, well, I'm a tennis player. I really like to understand more about arms and hands, so I think I'm going to work on hands.
So this is the hand that Yoki built for her master's thesis. It fiddled on the end of an arm for COG.
It was the first robotic hand that Yoki ever built.
Yoki used to always surprise me because she would go into a field where she knew nothing, really. And within 3 or 4 weeks, she'd be knowing everything about it and making contributions there.
She thrived in this new field, but Yoki was still hiding. She wouldn't even buy books because she was afraid of seeming smart.
Second year graduate school at MIT, I had to put a name tag, and it says, hello, my name is, and I'm supposed to put Yoki on it. But I thought it'd be really cool if I put airhead. And I looked around at everybody's faces, and I didn't see all positive, like, yeah, girl, go, girl. My advisor, Rod Brooks, came and basically pulled me on the side and said, look, Yoki, this is not going well. Stop acting like an airhead. It's not going to take you far as long as you're acting this way. And that's the day that it really hit me hard and thought, wow, now I understand. Okay, I'm going to stop doing this. Acting an airhead is not the right dual life that I should be living in anymore. That was one of the few turning points in my life.
Now, 10 years later, Yoki has her own lab at the University of Washington and is working on a new robotic hand. Except this time, it's a robotic hand for humans.
Hand is really amazing. Hands set us apart from other species. We built this society because we can use tools. So that means that people who are disabled and can't use their hands, they're not given back this full human capability. I really want to give that function back to those people.
Yoki is building a prosthetic hand that will look and move exactly like a real human hand.
The index finger, for example, has 7 muscles. That means we need 7 motors to control and make it work exactly like a human finger would. When the motor moves, it pulls these strings just like a puppet, and the finger will then move in the correct way.
They use infrared cameras to track exactly how the muscles in the hand move.
We put reflective markers on an object, say your finger.
As I move my finger and record the motion itself, I can play that back using my robotic finger. So if I curl my knuckle joint, then I can make the robot to curl the knuckle joint the same way.
As you tense and release your muscles, they actually generate electrical activity. And so we're trying to tease out some of the different ways the brain controls our fingers and our muscles as we're trying to do a certain task.
One day people are going to be walking around with a prosthetic hand, which nobody can tell it's prosthetic. It moves like it looks like it's controlled naturally from the brain. That's how it's going to be. I really wanted to be somebody who sticks out, be different, have an attitude. If people said, hey, you have an attitude, I think, to me, that's a compliment.
And with her mathematician husband, Simon, Yoki lives this attitude, both inside and outside her lab.
I am the first generation who is openly having this dual life and saying, you know what, I'm not going to wait till tenure. I'm going to start having my kids. And it's really exciting, but it's really, really hard.
Using her MacArthur Genius Award money, Yoki's on a mission to pave the way for the next generation of women in science.
What I really would like to do is to change the image of math and science. Volunteer for using this hand and the robot. And if I could really change that image, then it's okay to be smart, and it's okay to be a girl and then still be able to pursue math and science, and it's accepted. We'll put even the skin on it and the skin color, everything. I'd like to be a role model, and I want them to see that that's what I'm doing and to achieve that, and then do better than me.
As we travel around by car, we expect the bridges we have to cross to be safe and secure. But many of them are very old, and a few have already collapsed. Wouldn't it be great if engineers could create a technology so that bridges could tell us what's wrong and how to fix it before it's too late? Correspondent Peter Standring reports on efforts to prevent another tragedy like the one that happened in Minneapolis not long ago.
Minneapolis, 911. The bridge collapsed. People are stopped up on 35. The whole bridge fell into the river.
At the end of rush hour on a hot summer day in Minneapolis, Minnesota, a major bridge over the Mississippi River suddenly collapsed.
There could be people trapped in cars. In the river, there are cars sinking and people in there.
We know, ma'am. Everyone's on the way.
Over 100 cars fell with the bridge. Among them, a community center school bus carrying 54 children.
And then all of a sudden, out of nowhere, it was just this big drop. We'd all hit our heads, come back down, hit our heads, come back down. You just heard kids screaming, oh my God, what happened, what happened?
The disaster killed 13 people and seriously injured over 100 more. And if this bridge collapsed, what about all the others like it across the country?
We have 76,000 structurally deficient bridges in the United States. That's almost 2.5 times as many as we had 20 years ago. And we need more modern, non-destructive technologies to inspect those bridges today to make them safer for the future.
The cause of the Minneapolis collapse is still under a federal investigation, but here's what we know. The Minneapolis Bridge was an underdeck truss arch design made up of twin trusses of steel beams, arranged in triangles and connected with steel plates called gussets. The trusses distribute the weight of the traffic throughout the structure, all the parts working together. But the design has no backup against failure. If one major part fails, the whole bridge can come crashing down. Investigators found that 16 of those connecting gusset plates failed, resulting in the catastrophic collapse. The tragedy was seen as a wake-up call, highlighting the need for technology that warns us before a bridge fails, technology appearing on bridges even today. About an hour's drive east of Minneapolis along Interstate 94, you'll find this bridge spanning the Red Cedar River here in Wisconsin. It has an underdeck truss arch design that's almost identical to the bridge that collapsed. In fact, this one is 10 years older, so down below on its aging steel structure, crews from the Wisconsin Department of Transportation are installing sensors to give it a kind of high-tech physical. This will keep me in the basket?
It'll keep you attached to the basket.
Attached to the basket, okay. I'm not crazy about heights, but the only way to see for myself was to climb into the basket as bridge engineer Finn Hubbard took me up over the edge and under the bridge.
We're coming back now and taking a look at it with our sensors today to find out how the bridge is doing inside, if you will, looking at the stress and the strain, the forces inside the members themselves.
The sensors, called strain gauges, are welded onto critical spots on the bridge.
What that does is it actually measures the strain, which is the actual stretching of the metal, sort of like stretching a rubber band.
The gauge is attached to the bridge so that when the steel stretches, the gauge stretches, changing its electrical resistance. By comparing the gauge's readings to the way the bridge is supposed to perform, Finn can tell if the metal is overly stressed. And do you think ultimately this is making for a safer bridge, or at least is going to give you the information that you need to keep it safe?
I think what it's going to do is give us that added measure of insurance that the bridge is behaving the way our computer model back in the office is saying it is.
But strain gauges have serious limitations. They can only give you one type of information at one spot on the bridge, and they can't warn you of an imminent collapse. If we could only probe deep inside an old bridge's inner structure to find out which are in danger and which are sound, well, it turns out we can. The same way that submarines detect other boats, using the echoes of sound waves, or sonar. At the University of California, San Diego, they're using a kind of sonar technology to find cracks in bridges. They're called piezoelectric sensors, and they can both send and receive high-frequency tones right through a bridge.
So this one will launch a wave into the structure, while this white one here will then detect the signal at the other end.
The wave is ultrasonic, so Eric's computer converts the signal so that we can hear it.
All right, so what we have here is our signal that we received on the healthy structure plate. And if we downshift that ultrasonic signal to the audible range, this is what we hear. Very nice, clear tone.
But if you fracture that steel plate, the crack forces the ultrasonic waves to take different paths.
Now we replace that healthy beam with a damaged beam. Put the same sensors on it and apply the same signal again. This is what we get out. You can both see the difference and hear the difference, these extra tones that are now present in that damaged plate.
So how would that work on a bridge? You can place a bunch of these devices around trouble spots like gusset plates, and then have them ping each other in different combinations, probing for problems such as cracks in the structure.
What we do is we deploy arrays of these, many of these on a structure, and then we launch waves and we listen. And the idea then becomes, if you keep doing that test and a crack has developed, maybe corrosion has occurred, a bolt is coming loose, or the signature that we're detecting is going to fundamentally change.
But the ideal technology would not only probe for damage and signal its location, it would literally show you where it's broken. At the University of Michigan, researchers have developed a nanotech skin that could one day cover and monitor bridges 24/7. Here, they've successfully tested a coating that, when stimulated with an electric current, senses damage beneath its surface. And the secret of the sensing skin is the new wonder material of nanotechnology, carbon nanotubes. Carbon nanotubes are microscopic tubes of carbon atoms that join up under extreme temperatures. Many times stronger and lighter than steel, carbon nanotubes are also amazing conductors of electricity. And it's the electrical properties of these tiny tubes that make the sensing skin possible.
The honor is all yours, Peter.
Breaking the skin. Here we go.
Excellent.
To test the system, Professor Jerry Lynch let me punch holes through a steel plate covered with nanotech skin.
So with your incredible strength, you can see that you punctured all the way through the plate.
The electricity passing through the skin creates a high-resolution map on a computer, providing a visual representation of the puncture holes.
So the magnitude of damage would be correlated to the color coding that we have here on our images.
The skin could be sprayed or glued over critical bridge components. When damage starts to form, the skin's electrical current is forced to flow in different directions, change that a computer reads and displays as damage. And by altering the chemistry, different layers of the skin can be made to detect different types of damage. Deformation, cracks, corrosion, all at the same time, catching threats before they become dangerous.
Could you envision, a bridge engineer sitting in his office monitoring the well-being of a structure through a system like this?
Yes, that's one of the beauties of this particular technology, is how self-evident damage appears in these images.
Within months of the Minneapolis collapse, construction on a replacement bridge is already underway.
This bridge is a big responsibility for restoring confidence. We expect our bridges to be safe and to get us where we need to be every day.
The new bridge is being built of high-density concrete, and its design includes multiple backups against failure, and what's promised to be a state-of-the-art sensor system.
The main concept is to have many different technologies working in concert. And collectively, these will all work together to bring us the best data for the bridge.
But even as the bridge takes shape, the scene evokes mixed feelings for Julie and Sasha.
I think this might be the only bridge that I may feel comfortable going across because it is a new structure.
The new bridge, no matter how many times I cross it, for me, I'm never gonna get the sounds and the sight out of my head from the actual bridge collapse.
Now for some final thoughts on the Northern Lights. Who would have guessed long ago what causes the aurora? Countless atomic and subatomic particles released by the sun in resonance with its 11-year cycle stream among the planets at speeds up to 1 million miles an hour. These charged particles see and respond to Earth's magnetic field. The positive and negative charges split north and south. They then gather and pulse in ways still mysterious as they collide with molecules of Earth's upper atmosphere. The collisions render the air aglow, creating one of the most colorful and striking sights of the Arctic night, as the sky fills with dancing curtains of light. No doubt about it, the aurora is complex. To understand it requires a branch of advanced physics called magnetohydrodynamics, a field that's been known to make strong men weep. Meanwhile, Aurora has been and continues to serve as a fertile source of art, mythology, and legend among Arctic peoples and their visitors, as it leaves viewers in silent awe of its majesty and beauty. It's a curious thing about the universe. Behind the most stunning phenomena to behold lies some of the most challenging problems in astrophysics. From the colorful turbulence within planetary atmospheres, to stars in the throes of death, to the majestic patterns of spiral galaxies, to the large-scale structure of the universe itself. What distinguishes the aurora among them is that you don't need a telescope to see it, just your eyes and a ticket to the Arctic. And that's the cosmic perspective.
Educators and other educational institutions can order this NOVA program for $24.95 plus shipping and handling by calling WGBH Boston Video at 1-800-255-9424. NOVA is a production of WGBH Boston.